Yeah, basically today we're going to practice, or we're going to learn how to do, we're going to use these generating functions to solve more difficult versions of these integer solution questions. So you remember these ones? So I think there was something like this in the assignment, maybe assignment 2, I guess, and possibly even on the test. Actually, on the test, it was an easier version than this. But remember when we had these questions where you have a bunch of variables, let's say y1 up to y4, and we're assuming y2, y3, y4 add up to 14, and we have a lower bound on yi, but also an upper bound. Okay. Do people remember these things? And the way we were solving them using inclusion-exclusion to just look at all the solutions where we don't have any upper bound, right? We just assume this, and then do some inclusion-exclusion. So you want to subtract the solutions one is too big, and then subtract the solutions where y2 is too big, y3, y4, it's, and then add in the solutions where they're both, and so on. Remember these things? I don't know. Okay. So what I want to do next is to show you a way to solve them without, so we're not going to directly use inclusion-exclusion, we're going to use generating functions. The cool thing about this is that this method is going to be able to be extended to other types of questions, which are questions, so then the other types of questions will be things that we haven't seen before. So let's solve this using generating functions in inclusion-exclusion. Okay. So just repeating our equation, this is what we want to find the solutions to. I's are integers. Okay. So let's imagine we didn't have the restriction I is at least 1. Then the answer to the question to the coefficient of x to the 14 in this thing, where I take x plus x squared, x cubed, x to the 4, x to the 5, that. So I'm claiming that the coefficient of x to the 14, when you expand this, will be the number of integer solutions. So the coefficient in this thing is equals the number of integer solutions to y1, y equals 14, such that all the yi's are at least 1. Okay. And you can kind of think of this, so why is the coefficient of x to the 14 in here equal to these solutions, right? It's because how do I get x to the 14? Well, I get it from taking x to some power times, so let's say x to the times x to the y2, so y1 the first factor, right? Because I've got 4, I've got this thing basically written 4 times. I get y1, an exponent of y1 from the first one, y2 from the second, y3 from the third, y4 from the fourth, such that y1 plus y2, y4 equals 14. Right? Yeah, so I'm not sure how to make this crystal clear, but the coefficient of x to the 14 in this thing, in the expansion, will count integer solutions. with this restriction that y is at least 1. If I want to change the question of a restriction that yi is at most 5, change my generating function thing. So what I'm saying is, instead of having x plus x2, x squared, x cubed, x4, x5, x to the 5, x to the 6, x to the 7, off to infinity, to the 4th power, what I want to do is change this to something else, which will take into account this restriction that y is at most 5. So does anyone see what I should change it to? Exactly, yeah. So use powers that are bigger than 5. So what I should do, so then therefore the number of solutions to my will be, I want the of x to the 14 and x plus x squared, x cubed, x to the 4 plus x to the 5 to the 4th power. Okay. Okay, and that's going to basically do the same thing as restricting y, because the exponents are all at most 5 and at least 1. Okay, now how can I write this? So a lot of this generating function is about recognizing kind of patterns and recognizing ways to rewrite kind of expressions. So yeah, so here's the thing. So I know this is kind of the most fundamental generating function that we're going to see in this course is this one, right? A lot of stuff we do, maybe not everything, but a lot of stuff we do can really be boiled down to manipulate this function. So if I want to represent x plus x squared up to x to the 5, what I can do is subtract two different kind of manipulate function. So what I can do is I can take x over, which will give me all the powers of x except for the 0th power. So it gives me x plus x squared plus x cubed all the way to infinity, big powers. So I subtract. So this one's x to the 6 plus 7 plus x to the 8. And both of these, the equation here and multiplying it by x or multiplying it by x to the 6. Okay. So now let's do a little bit of algebra. So I'm going to factor. So here, remember I've got this 4th power, so don't forget that. I factor out x over 1 minus x from the inside, and I factor it all the way out, so that's like factoring out x over 1 minus x to the 4th, right? Like what I get is over 1 minus x times x to the 5, right? Okay. Is it clear how I got this? Factoring. It's probably not clear yet why we're interested in this, but it's going to be kind of nice. Okay. So this is something I can deal with. So let's deal with the two different factors, the two different parts of this individually, right? So I'll look at this one and I'll look at this one separately. The first one, by the way, I mean, that's just what you get by, the first one can be right. And actually we've also got an expression for this before, right? So this is that expression before, we know exactly what this thing is. You get from the binomial theorem, right? Binomial theorem lets you expand x plus y to some power for those things. So the first one, we remember our trusty formula that, this is the sum from any 4 minus 1, which is put that in here. Okay, the fastest thing to do is to remember this formula, I guess, from, so it's, remember binomial theorem, right? So this is the sum from n equals 0 is the power here of -1 choose n, x to the 5n, right? So this is, to get this, I'm just doing a sort of substitution in the binomial theorem by letting one of the variables be 1 and one of the variables be, so this is just the binomial theorem. Looking at is this product, right? And remember there was this formula, the coefficients of x and the product of two different generating functions. So to remind you of that, so the coefficient of x to the 14 here is, so you add up from 0 up to 14. So k equals 0 up to k equals 14. In the first, so the first expression, so 1, this you take the exponent of 14 minus k in 1, and you multiply that by the in 2, where 2 is, and you do that for k equals 0 up to 14. Okay. So I mean, this is using like something we derived last time, but also if you just think about it, like it's kind of clear, right? If I want to make a 14 in the exponent, I have to take, you know, something like 14 minus k exponent from here, and I have to take a k from here and put them together. So it's the coefficient of 14, x to the 14 minus k, x to the k, and then you have to add that up over all values of k. Okay. And then you notice here that the only exponents that have a non-zero coefficient in 2 are x to the 0, x to the 5, x to the 10, and x to the, right? So all we have to do is look at those terms, 5, 15, or 20, but actually 15 doesn't work because we're only from 0 to 14. We have to look at k equals 0, 5, or 10. And then we just plug in the coefficients. So when k is 0, the coefficient of x to the 14 and 1 is, so if I plug in n equals 14, I get 13 choose 3. From 13 choose 3 times 4 choose 0. Now, the next k we have to deal with is k. The coefficient of x to the 9 is 8 choose 3 in 1. The coefficient of x to the, x to the 5 is 4 choose 1. And then this is similar. So, and then there's a minus sign to work this out. Choose 3 is the coefficient of x to the 4 in the first one, and this is the 10 in the second expression. And this is your final answer. Arguably, that's more complicated than just doing the, but if you check, it gives you the same answer, and it's kind of a nice algebraic way of doing things. So I understand that. I think each individual step is not too bad, but putting all these steps together is what's going to be difficult. So just to kind of recap, what did we do? So the bottom summation, actually maybe I should restate this in general. So So here's what I'm using in the bottom summation. I'm using this kind of proposition that, let's say f of x is the sum from infinity of an x to the n. And let's say that g of x is the sum n equals 0 to infinity bn x to the n. What I'm using is that the coefficient x times g of x is equal to the sum from k to n, ak, b, n minus k. So this is just a basic fact about which is not hard to prove. And I expand it out. How do I get x to the n? Well, it comes from, to get x to the n, I have to get, let's say, x to the k from here and x to the n minus k from here for some k. And when you do that, the coefficient you get is ak times n minus k. Like if I take the x to the n minus k term here and the x to the k term here, I get a coefficient of ak from there and a coefficient of bn minus k from here. And so that kind of contributes to the coefficient of x to the, but that you have to sum that up over all different values. So that's all I'm using here. And I'm applying that in the case where f of x is, so f of x is x over 1 minus x to the 4 is 1 minus x to the 5 to the 4. Right, so if we can work out, so we worked out the of this thing, and the coefficients of this thing, coefficients of the product is. And so that's all I'm using here. It's this thing in the first one, and so x to the 14 minus k here, and x to the k, and we add those all up. Okay, but thanks for asking that question. I think it's probably the case that people won't have remembered that from last time. Okay, so we're going to basically do another example here. We're going to, keep doing examples until we understand this, I guess. Until we run out of time, which is probably going to happen first. But functions, and this is going to be a more complicated version. Okay, but if you didn't understand the last one, kind of by seeing it again, maybe you'll have a better chance to understand it. So suppose that a fruit basket must contain at least one apple. Okay. And a number of oranges which is divisible by 4. And it can contain any number of bananas. So it can be 0 bananas, 1 banana, 2 bananas, however many bananas you want, and no other type of fruit. And now the question is, how many ways can I make a fruit basket size n? Size n means, n fruits in total. An apple, you always have at most 3 pairs. Number of oranges is bananas, and you don't have any other type of fruit. So these are the only types of fruit. Can I do it? And we want to do this using generating functions. Okay. So can anyone, so I want to write this, express this as finding the coefficient of x to the n in a generating function. So the generating function is going to have one fruit, the thing that I write in the apple parentheses here. So by the way, this whole thing breaks down to integer solutions, right? Basically we want, so if y1 corresponds to apples, we want solutions to y1 plus y2 plus y3 plus y4 equals n, right? Where y1 is at least 1, y2 is between 0 y3 y4 is anything at least 0. Right? So first of all, is it clear that this is the same thing? We're counting solutions, integer solutions to this, where the y1 is going to be the number of apples, y2 is the number of pears, the number of bananas. Integer solutions to this equation with these constraints. What should I make the function I write for the apples? Like with some, so it's going to be some sort of thing involving x's. Okay, so maybe I'll give you this one. So I'll say, so this one's going to be x plus x squared, x cubed, off to infinity. Because, so I start with x because y1 is at least 1, right? So the y's kind of correspond to the, and so this is the thing that I put in, represent the number of apples. So what's the function that I should put in for pears? Good, right. So 1 plus x, and basically the contribution from this term, number of pairs in the solution. So y2 is like the exponent of x that I get from the middle factor, or sorry, this green factor. What about oranges? Okay, bananas are easier. Let's do bananas. So bananas is just going to be x squared, x cubed, 0. What about oranges? This is kind of a weird one. So yeah, totally. So because the that corresponds to the exponent I get from the from this factor, which to the number of oranges. So there's either 0 oranges or 8 oranges or 12 oranges all the way to infinity. Okay. When you're trying to do these problems using generating functions, the first thing to do is, if it helps, you can write down, a problem, an integer solution problem, but you don't necessarily have to write down. You can probably just go written if you write the function in this kind of way, right? But now I want to simplify this, and eventually I want to work out the coefficient of x to the n. So that's going to be just a lot of algebra, similar to what we did before, but things are going to be a little bit more complicated. Okay, so I can write these things. I can write these things kind of using that you should never forget that 1 over 1 minus x is the sum, 1 plus x squared, etc. Right, so the first factor I get by just multiplying this by x. So, right, so this is just x over 1 minus x. The second one, similar to what we did before when we were doing inclusion exclusion, we took, so, if I take 1 over 1 minus x, that gives me 1 plus, infinity. If I take that thing times x to the, that gives me all the powers that are bigger, that are 4 or larger. So if I subtract this one from that one, it'll cancel out x to the 4, x to the 5, etc. So I can write this green thing like, and I can write this one as 1 over 1 minus x to the 4 by doing a substitution, right? So if I let, if I let y equal x to the 4, then I've got 1 over 1 minus 4 is 1 over 1 minus y, which is equal to the sum n equals 0 to infinity of y to the n, which is the sum n equals 0 to infinity of x to the 4n. So that's how I get from this to this. And then the Benez is just 1 over 1 minus x. Now, in this example, something magic happens. Not always going to be how it goes, but we get lucky in this example. So the numerator here, so this green thing is over 1 minus x, right? Numerator here, you see it cancels x to the 4 on the top. In the orange term, I have 1 minus x to the 4 on the bottom. So those cancel out. Extremely lucky, okay? More complicated examples later, but this is luck. Your life is a little bit easier. So, okay, so what happens after you cancel? So we're left with, so what do we, yeah, what we get in the end is x over 1 minus x from the first term. From the second term and the third term combined, right? The numerator here cancels the denominator, so we get 1 minus x from there. So we get x over. So is it clear how I got this with the cancellation? So all I did was cancel the 1 minus x to the 4 on the top here with the 1 minus x to the 4 on the bottom of the other one. X cubed. And now we're going to step x cubed over 1 minus x cubed is this sum. So it's the sum of n minus 1 choose 3 minus 1 choose 2 x to the n. Basically the same as this, right? Except that there's fewer x's here. So basically it's the sum n equals 3 to infinity, n minus 1 choose 2. X has, this one's an u down here. Okay, and that's to take into account the fact that there's no exponent here, 1, and the exponent up there is 3, right? X is x to the 1. And now I can rewrite this sum starting at 1. So what is this thing? So this is the n equals 3 term is 2 choose 2, x to the 3 choose 2, x to the 2, plus 4 choose 2, x to the, and if you think about it, this is going to be, so the general term here is, so if the exponent is infinity, I have x to the n, and the coefficient is n plus 1 choose 2. Right? Is that clear? This is another thing that you need to get used to, is manipulating these generating functions by changing the summation. Right? Here we're summing from 3 to infinity. And we can write that, we can rewrite the sum. Basically, this is doing a substitution in some sense, right? So if I kind of think of m as being n minus 2, then I can rewrite the sum as m goes from 1 to infinity, m plus 1 choose. So, of course, it doesn't matter if I call m or n, so this is just like, so these are the same. So if you want doing this, changing the index, yeah, this is a way to do it. If you kind of substitute m equals n minus 2, and then rewrite the sum in terms of m, and then rewrite that in terms of n. So the number of fruit baskets of size n is n plus 1 choose 2, because that's the coefficient of x to the n. So is it clear, or any questions about that? I feel like with these problems, the first step is kind of natural. You turn it into a generating function. But I feel like by the end, when you've got the solution, so we've got the solution n plus 1, choose 2, it feels like you've forgotten what the problem was, because you've done all this algebra. But remember, we're counting the number of fruit baskets, and the number of fruit baskets of size n is equal to, that's what we found, and so we found the number of fruit baskets. Any questions about this? So basically, if I wanted to give you a recipe for how to do this, right? Take your question, write out the generating function by doing, so like we did here, by saying, you have this, the first factor counts the number of ways to choose the first thing, like apples, then the second one counts the second thing, third thing, fourth thing, and so on, right? And then from there, just start doing the algebra, right? So you can do some substitutions, you can do, you can, this kind of trick here, where you subtract things. You've got this kind of trick where you do a substitution, and this kind of trick where you just multiply by power of x, and then just start doing the algebra to try to simplify the coefficient of x to the n. And then when you find the coefficient of x to the n, that's the answer, saying that like the xi is divisible by 4, for example. But now we know how to do that. Okay. So let me give you, so the cancellation of 1 minus x to the 4 canceled with 1 minus x to the 4 in the denominator. What I want to do now is give you an example where cancellation, so you have to do something a little bit more complicated involving partial fractions. Okay, so let's count integer solutions to x1 plus x2 plus x3 such that x1, x2 is at least 0, so any number at least 0, x3 is between 0 and 2. So these are our constraints, and we're counting. So we're looking for so don't be confused about so I'm using x here, x in the generating function. So hopefully that's not too confusing. But how would I write the generating function for this? So I'm looking for the exponent of x to the, and how do so what should I write in these 3 parentheses? So the first one's going to correspond to x1, the second will correspond to x2, and correspond to x3. So what you want, oh, sorry, yeah, you're right. This is just, yeah, sorry. The exponent of x to the n is obviously n, the coefficient. Sorry if I sometimes get the words mixed up. Yeah, thanks for correcting. First thing here to correspond to x1. So what should I write here? So the exponent of x1 can be any number that's at least 0, or sorry, the 0, 1, 2, etc. So here I want the exponents to be 0, 1, all the possible values for x1. Oh, sorry. I feel like I must be half asleep today. x1 is even. So the possible exponents for x1 are 0, or 2, or 4, 6, etc. x2 is at least 0, which corresponds to the generating function 1 plus x squared plus x cubed. x3 is between 1 or 2. And the coefficient of x to the n here will count solutions to x1 plus x3 equals n such that, you know, these things hold. Okay. Basically, the contribution will correspond to the choice of x1. Contribution from the second term will be the choice of x2. And the contribution from will be the choice of x3. And the exponents have to add up to n in order to contribute. Okay, I'm not sure. Yeah, okay. So then maybe not simplify. Well, we want to do something to this. So the first term can be written as 1 over 1 minus x squared. Because, yeah, by doing a substitution, minus x. And the third term just is, I mean, well, how did I want? Yeah, I mean, you could. Well, for now, I'm just going to leave this as 1 plus x squared. Now, this one you could read 1 over 1 minus x cubed over 1 minus x. I'm not even completely sure why I'm not doing that. But let's leave it as this for now. We might do that step later. Let's see. But for whatever reason, the way I wrote these notes, I decided to leave it as this at first. So what we're dealing with here is 1 plus x squared over 1 minus x squared. So like 1 minus x squared is 1 minus x, 1 plus x. So I can replace this by that. 1 minus x 1 combines with this one, and squared 1 plus x. Okay. So this is the expression I've got so far. Right. So do you remember something called partial fractions? That was where, I don't know, you have something like this and you want to write it as like something over 1 plus x plus yeah, unfortunately it's coming back here. You might have thought in a discrete math course you wouldn't see anything related to calculus or related to what you saw. And then how did it work? C over like 1 minus x squared. Remember, if you have like a, on the bottom you have like a something and then you have something else where it's squared, you do, you know, 1 plus x, 1 minus x, 1 minus x squared. I think that's how it works, right? So this can be written like that. Okay. And then you want to solve for a and b and c. And the way you do that is by multiplying things out, right? So you, so if I multiply this out, I just take this denominator and I multiply it to everything. Left side, I just get the numerator. On the right side, I get a times 1 minus x squared because the 1 plus x cancels. Then I get b minus x, and I get c 1 plus x because of cancellation. The terms, corresponding to different powers of x. So I get an a from here. I get a plus b plus c. So I'm kind of here, right? Because I mean, so I could as a 2a x plus a x squared, right? I can write this, I can write all of these things out. This is b minus c. And then if I collect up the terms based on the power of x, so the constant term is a plus b plus c, a here, b here, c here. The thing with an x is negative 2a plus c, and the coefficient of x squared is a minus b. And we need this thing for all, because there's a 1 here. This thing has to add up to 1 because the coefficient of x here is 1. So I write this system of equations. And I guess probably know how to solve systems of like 3 equations. Eventually you'll get to the solution where a is a quarter. So this is, I don't know, linear algebra, or but probably you did this in calculus as well, just solving, and you end up with this 3/4. And okay, so therefore our generating function, which was equal to this in this way, with this value of a, b, and c. Okay, and the good thing is that these deal with, right? Because these are just basically these basic building blocks that we've looked at before, right? This whole thing about how 1 minus x is just the geometric series. I mean, so 1 over 1 again is 1 plus x squared, etc. Basically, all of these terms are just some version of that, right? This one is, yeah. So this one is like substituting a negative x in there, and then I've got a quarter times negative 1 to the n x to the n. This is 3/4 times the geometric x to the n. Using like the derivative of this thing, which, yeah, or we're using our formula that this thing is n equals, if I take that to the power k, n equals k to infinity, n minus 1, choose k minus 1, x to the n block here, but it can also, and that's all we're using here. And here I've got an n minus 2 because there's no x squared on the top here, right? So it's kind of I take this expression, I divide that, subtracts 2 from the exponent. And so if you kind of thing to write it in terms of x to the n, what is the sum n equals 0 to infinity, n plus 1, choose 1. Obviously, n plus 1, choose 1 is just n plus 1, x to the n. So here I've just changed index of the summation. So as a final answer, the coefficient of x to the n is the combination of these 3 coefficients. So it's n minus 3/4 plus 3 n plus 1 over 2, which is a bizarre answer. But this kind of shows you the magic of generating functions. We wrote down a function. The n is the final answer. And then we just manipulated that function until we could write it in a simple way that we can understand the coefficients. And this is the number of solutions to the original question, which was like, which one? This question. So the answer to this question is negative 1 to the n over 4 minus 3/4, I think, plus 3 n plus 1 over 2 is the number of solutions. I think that, right? 3 n plus, yeah. which, yeah, I don't think that's something we could have done using the tricks we've developed so far in the course. Are there any questions about this example? To be honest, I have a didn't. What would have happened if we would have written my 1 plus x squared as 1 over 1 minus x cubed over 1 minus x, right? We didn't do that, but it wouldn't have been wrong to do that. I'm just not sure where it would have gone, though. So maybe we can think about that. But actually, this. So maybe I'll do that separately, and we can, yeah, I'll figure out what to do with that. I'm kind of interested to know it because I don't want to, yeah, I want you to have a systematic way of doing these things. Anyway, but, so I'll kind of do that separately. Okay. So here's one thing. So I want to test, can you come up with the generating function? So let an be the number of integer solutions to this thing where we take, so x1 plus x2 plus x3 plus x4 is n. We have the restriction that, so x1, x2, and x3 are at least 0, and x4 is a multiple of 3. So which of the things in the poll give you a generating function, the number of solutions? So give you a little bit of time to thought. Do people know Jeopardy? That's the theme for the thinking song for Jeopardy. I don't know if your generation knows Jeopardy or not. Okay. So, right. So let me kind of start doing it. First 3 exponents should be 0 or 1 or to infinity. So you get one of these things. So that's that thing cubed. Then this one's supposed to be a multiple of 3, which means I've got like 1 plus x cubed plus x to the 6, dot, dot, dot. And that's going to be equal to, by substitution, that's equal to 1 over 1 minus x cubed. So the answer should be, yeah, 1 over 1 minus x all cubed times 1 over 1 minus x cubed, which I think was the most popular answer. I apologize that it's a bit hard to parse written like this, but so that could have been the part of the problem. But yeah, so this is the answer here. Okay. That's not particularly interesting. Okay, here's a question. Let's so how so this is a kind of question that you could be asked, to create a combinatorial problem that gives you this generating function. Okay. So maybe let me, so, right, I think the easiest is to just make it like counting integer solutions. Well, let me kind of collect some things up here. So, so okay, my 1 plus x squared plus x to the 4 is kind of special. I could write this as x over 1 minus x squared. So I'm trying to deal with the stuff on the numerator. So I've got this one, and then I've still got stuff on the denominator. So I can write this as minus x, 1 over 1 minus x cubed. Sorry. And then 1 over 1 minus x. To, let's say, I don't know. So I've got 1, 2, 3. So 1, 2, 3, 4, 5, 6 different variables, like, so y1 plus y2 plus dot, dot, dot up to y6 equals n. The first one, so y1 is either 0, 2, or 4. Y2 is at least 1. So this one is corresponding to y1. So I want to do this thing. So the 1 comes from the fact that x over 1 minus x. So y4, we want to be just at least 0. Y5 divisible by 3. And y6 divisible by 10. Okay. The coefficient of x to the n in this thing will count the integer solutions to this question.